Welcome to today's presentation on designing for maintainability. In this session, we will cover the key principles and best practices to ensure that our system remains sustainable, easy to maintain, and evolves efficiently over time. Here's a quick overview of what we will be discussing today. First, we will explore code modularity and why breaking down our system into independent components is so important. Then we will dive into separation of concerns, helping us to better organize our system's functionality. Next, we will talk about testability, ensuring our code is easy to test and maintain. We will also discuss code review and pair programming, collaborative techniques for improving code quality. Then we will cover documentation standards to ensure our system is well documented for ease of understanding. We will touch on version control as a means to track and manage code evolution. After that, we will look at refactoring, a technique for improving code quality without changing its functionality. Finally, we will wrap up with monitoring and logging, essential tools for tracking system performance and issues. Let's start with code modularity. Modularity involves breaking down our system into self-contained, independent components. This is essential for maintaining a clean architecture and making our system more manageable. The key principles of modularity include the single responsibility principle, ensuring each component has one job, and cohesion, which ensures that related components are grouped together. On the other hand, loose coupling minimizes dependencies between modules, making them easier to modify independently. The benefits of modularity are clear. It makes our code easier to debug, test, and scale, while also supporting parallel development efforts. Next, let's talk about separation of concerns. This principle means organizing our system so that different concerns like user interface, business logic, and data storage are kept separate. One common approach is to use a layered architecture where each layer handles a distinct responsibility. This improves clarity, reduces interdependencies, and makes it easier to troubleshoot and extend the system. Separating concerns also allows each layer to evolve independently, which is crucial as our system grows. Now let's discuss testability. A maintainable system must be easy to test. By ensuring our code is testable, we can catch bugs early and verify new changes without fear of breaking existing functionalities. Some key features include dependency injection, which makes it easier to inject mock dependencies for testing, and test-driven development (TDD), where we write tests before writing the actual code. Mocking and stubbing are other strategies used to simulate real-world conditions in unit tests. A testable system is easier to maintain because we can identify and fix defects quickly, ultimately improving the stability of our code base. Next, let's discuss code review and pair computing. Code reviews are a collaborative process where developers review each other's code to catch issues early and ensure quality. Regular reviews not only help improve the code but also spread knowledge across the team. Pair programming is another collaborative technique where two developers work together on the same code, providing real-time feedback. This improves problem solving and accelerates learning. Both of these techniques contribute to higher code quality and foster team collaboration. Moving on to documentation standards, proper documentation is key to ensuring that our code can be easily understood by other developers or even our future self. There are three main types of documentation: technical documentation, such as architectural diagrams or API specs, code comments which explain complex logic, and user documentation which guides end users or administrators. Best practices include keeping documentation up to date and using clear, concise language that anyone can understand. Now, let's talk about version control. Version control systems like Git track changes to our code base, allowing us to manage and revert changes as needed. Best practices for version control include writing clear commit messages, making small incremental changes, and using feature branches to develop isolated features. Version control not only helps in tracking changes but also enables collaboration, ensuring multiple developers can work on the same code without overwriting each other's work. Next up is refactoring. Refactoring is the process of restructuring our code to improve readability and maintainability without changing its behavior. Common techniques include extract method, which simplifies large functions, and renaming variables to use meaningful names. Removing duplicate code is another important technique to consolidate similar logic into a single function. Refactoring reduces technical debt and makes our code base easier to modify as new features are added. Lastly, let's discuss monitoring and logging. These practices are crucial for detecting and resolving issues in real time. Monitoring tools like Prometheus or Grafana track system health and performance, while logging systems like ELK-Stack or Splunk capture detailed information about our application's behavior. Using structured logging helps us easily parse and analyze logs. These tools allow us to proactively address issues, minimize downtime, and ensure our system runs smoothly. In summary, maintainability is all about designing systems that are easy to manage, evolve, and troubleshoot. By focusing on modularity, separation of concern, and testability, and leveraging practices like code reviews, pair programming, and refactoring, we can create a more maintainable system. Additionally, version control, documentation, and monitoring provide support for long-term system evaluation and reliability. Thank you for your attention. I hope this presentation has provided you with valuable insights into designing for maintainability. If you have any questions, please feel free to ask.